Hey, this is Horner, and we're going to look at the second part of the oscillation section. And this is energy in simple harmonic motion. So we've got a mass, and this mass is moving left and right. It is attached to a spring. So as it moves left, it compresses the spring. It comes to an equilibrium point where it's neither compressed nor stretched, and then it comes over and stretches. There isn't any dissipative forces here at all, so that means there's no friction. And so you can kind of see what's going on in the picture here. When we get to the end, we have all potential energy, and in the middle we have all kinetic energy. So our total energy should just be a flat line. So this should be pretty easy to see. Remember, kinetic energy is 1/2 mv squared, and the elastic energy for this is 1/2 kx squared. So we're transforming energy from elastic potential to kinetic to elastic potential to kinetic, and then back and forth, and we do that forever. Energy is conserved in simple harmonic motion, so here are our equations again, and we notice that at plus or minus A, so wherever we have our potential here and our potential here, we end up with U, and that's really equal to negative Ka squared. So that's at anytime I have a positive or a negative. Anytime I'm at 0, then my kinetic energy is just equal to negative m Vmax squared. Let's go ahead and do this one. This is a quick check. So I have a block oscillating in a very long horizontal spring. Here's my graph. It shows the block's kinetic energy as a function of position. They want to know what is the spring constant for this one. And the spring constant for this one should be 4 newtons per meter. I know that 8 joules would be equal to 1/2 kx squared, where A here is my x. And if I rearrange and solve for K, I'll have 16 joules all over 2 square meters, and that would give me, sorry, that would be 2 meters squared, or 4 meters squared, and that would be 4 newtons per meter. The frequency for a simple harmonic motion, I know that when the kinetic energy is a maximum, my potential energy is 0, and when my potential energy is a max, kinetic energy is 0. So here I could just say that these are equal to each other. If they're equal to each other, I can find out what my maximum speed is. I also know that my maximum speed can be 2 pi times that amplitude, or 2 pi r is really what it is. So that's the circumference of a circle, or my distance traveled divided by the period in time. That's 2 pi f, which is omega, times the amplitude. So now we can say that our omega is equal to the square root of k over m. And our frequency would be 1 over 2 pi times the square root of k over m. So here is our overall equation. It is the period of a spring, or a mass oscillating on a spring, should be equal to 2 pi times the square root of m over k. So we've actually gone through and just done the entire derivation for the period of a spring and a mass oscillating on that spring. So here's just a really quick application. We know that the period is 2 seconds. If the amplitude of the oscillation is doubled, that new period should be 2 seconds. So you double one, you double. If I double the amplitude, that won't have any effect. I'm just giving it more energy, but it's not going to make it go any faster. Here I've got a block of mass m oscillates on a horizontal spring with a period of 2. If a second identical block is glued to the top one, now I've doubled my mass. And if I double my mass, my period then is going to be proportional to the square root of that mass. So I would just do the square root of 2, and then that would be proportional to my period. My original period is 2, so now if I double the mass, I'll end up with 2.8 seconds for that period. I have 2 blocks. They oscillate at different oscillate on different horizontal springs. Which spring has a larger spring constant? So you'll notice this one has a pretty high amplitude. The red one has a smaller amplitude. The red one also has a smaller period and a higher frequency. So this one's going to be the red spring, and it's because the frequency is proportional to the square root of the spring constant. So the one with the larger spring constant is going to be the red spring. Good example here. This is just using conservation of energy. I've got a 500 gram block on a spring. It's pulled a distance of 20 centimeters, so that is your amplitude. The oscillations then are 0.8 seconds apart. So they want to know at what position or positions is the block speed 1 meter per second, and then they want to know what is the spring constant. So here energy we know is conserved, and we're doing simple harmonic motion. So when we solve for this, we know the potential energy is equal to 1/2 Ka squared. So at maximum displacement, that would give me my total energy. At a later time when the position is x and the speed is v, now I can add the two together and that should be equal to this. So if we solve for x, x now is equal to the square root of a squared, that's our amplitude, minus mv squared all over k. And we know that if we have solve for omega here, we have v over, and then this would be m over k. So here we know that k over m is equal to omega squared, and that's from that equation 14.24. The angular frequency is really easily found then. I'm just going to do 2 pi over the period, and that'll give me 7.85 radians per second. So now I can plug everything into my equation. This is 0.2 squared. Minus 1 over 7.85. I have to square that. And I'm going to get two answers. It's going to be both 0.15 positive and 0.15 negative. So it has that speed on either side of equilibrium. We didn't require to know the spring constant. It's straightforward to be able to find it. We just use t is equal to 2 pi times the square root of m over k. We solve for k, and you end up with 31 newtons per meter. This is a dot diagram that we could do for simple harmonic motion. So here we notice that the speed increases as we go to the middle. At the middle it is the largest and then it decreases. We notice that our acceleration is going to the right and getting smaller. There's no acceleration in the middle, and then it grows as we get to the right. And then we're going to end up going back the other way. So you'll notice this is to the right, and then we come down here and this is going to be the left. Each one of the dots represents our positions. Acceleration is the time derivative of velocity. So if I have position here, if I find out what the velocity is, then I can do the second derivative, and that will give me acceleration. So in simple harmonic motion, acceleration is proportional to the negative of the displacement. So you'll notice that these are just inverse graphs here. If I want to look at the dynamics of simple harmonic motion, I know I have a mass oscillating back and forth on a horizontal spring. No friction at all here, so the spring force is going to be equal to negative kx. So that's how we typically have found our k value. Since the spring force is the net force, Newton's second law, we can say negative kx now is equal to max. So that is the overall force for the system. So now we can say A is equal to K over mx. Remember, K over m is omega squared. So our angular frequency here is equal to the square root of K over m. Quick check for this one. You have a mass oscillating on a horizontal spring. Its velocity, Vx, and the spring exerts a force of Fx. So here's the period. Is indicated by the area. So right at this time, we want to know, at this time, tell me what is the velocity, the magnitude of the velocity, and the direction of the velocity and the direction of the force. And so for this one, our Vx is 0 because it is turning around here, and our force is a positive. So our force here is a positive. Same thing, if we look at this position, now we can say that our velocity should be a negative because it is the derivative of this line, so it would just be the slope of the line, derivative of the position versus time curve, so that would be the slope of this line, and our force at this position should be 0. Vertical oscillations, as we've seen in class, are a little bit different. For this thing, the motion of a mass hanging from a spring is the same as it is for simple harmonic motion, but that equilibrium position is a little bit different. So remember, you can start at A and then move it down to 0, and it will oscillate between the two. And so here we're going to say that the change in length is equal to mg all over k. And here the string is stretched by delta L minus y. So let's go ahead and move on to the next one. It does give you an example problem. We have an 83 kilogram student hanging from a bungee cord with a spring constant of 270 newtons. The student's pulled down to a point where the cord is 5 meters longer than its unstretched length and then released. Where is this student and what is that student's velocity 2 seconds later? So this is equilibrium is right here. So our amplitude, notice, is not 5 meters. So 5 meters is where we've pulled it all the way down from where you have a spring that is not stretched. Okay. For this one, we know although the cord was stretched by 5 meters when we initially did it, it's not the amplitude. So that amplitude is actually going to be around this equilibrium position. So the cord stretch at equilibrium is given by this equation. So we're going to say delta L is equal to mg over k. If we pull all those together, we're going to end up with 3 meters would be our equilibrium point. So whole thing here is 5, equilibrium point is going to be at 3. So the student oscillates actually at a amplitude of about 2 meters. So this would be 2 meters, and then this would be 2 meters. It's going to do it at a point 3 meters below. So this is going to be 3 meters here. That is our equilibrium position. The student's position as a function of time is measured from that is 2 times the cosine of omega t plus that phase. Okay. And so here our omega is equal to the square root of k over m, which is 1.8 radians per second. So our initial condition must mean that our phase has got to be pi radians. And so at 2 seconds, the student position and velocity are the following. So here we've got 2 meters times the cosine of 1.8 radians times 2 seconds. So that's our time, plus pi radians, that's our phase constant. And so our y position here is 1.8 meters. The velocity at that is going to be negative 1.6 meters per second. So the student is 1.8 meters above the equilibrium, so they're about right here, okay, or 1.2 meters below the original end of the cord, so that's where the cord is there. Because the velocity is negative, he's past the highest point and he's heading back down. So negative velocity means you're going down, positive velocity would be here going up. So a block does oscillate on a vertical spring. When the block is at its lowest point of oscillation, its acceleration should be positive because it's moving. It's not moving up yet, but it is getting pulled up. There is a force in the upward direction. This is for pendulum, so we're switching from spring to a pendulum. Consider a mass that I have attached to the string. So here's my length of my string, here's my mass, and I make an arc length here. If I pull it back and let go, Newton's second law for that tangential component of gravity parallel to the motion should be the sum of the forces, should be equal to the force due to gravity at a particular time. And we know that that is negative mg sine of the angle. So here we've got our tangential axis. The tension only has a radial component is what we're saying. So this FGT is this FGT right here, and that's negative mg sine of the angle, and that should be equal to our mass times acceleration. Also remember this is the second derivative of our position versus time, and so here we should have negative g sine of the angle. If we look at a pendulum's oscillation at very small angles, we can use something called the small angle approximation. That is where the sine of the angle is going to be equal to just to the angle where that angle is measured in radians. So if we go back to our equation again, where we said the net force at a particular time is equal to negative mg sine of the angle, we can now just do negative mg of the angle. And that's going to be equal to mg over L times s, where s is that arc length. And now we can say that the angular frequency of the motion is found to be 2 pi f, and that's equal to the square root of g all over L. So that is for frequency. If we want period, we're going to do that one here in just a second. That's going to be a slightly different equation. So here's the 300 gram mass on a 30 centimeter long string, oscillates as a pendulum. It has a speed of about 0.25 meters per second as it passes through the lowest point. So that's going to be our maximum speed. They want to know what is the angle. So we're going to resume, just kind of think about that angle and know that it assumes, we can assume that angle is really small. And so here we've got simple harmonic motion. The angular frequency of that pendulum should be just gravity divided by the length, so we don't worry about mass. It doesn't have anything to do with it. We get about 5.72 radians per second. So its speed should be equal to the angular speed times the amplitude. We're going to solve for the amplitude here. That would be that arc length max. So here we've got, I'm sorry, that's that S max. That's V max over omega. And so when you divide the two, you get 0.0437. And then that maximum angle at the maximum arc length, which was S max, so there's our arc length maximum, is going to be the theta angle is equal to the arc length. So there's our arc length divided by the length of the string. We get 0.146 radians, and that ends up being about 8.3 degrees. So because the angle is less than 10 degrees, our small angle approximation should be very reasonable there. So here we go, we've got a ball and a massless rigid rod. It oscillates as a simple pendulum. If the ball is replaced with another ball having twice the mass, then that should have the same period. Okay, so remember, the only thing we worry about is how long this is. We don't worry about how heavy that ball is. On planet X, the ball on a massless rigid rod oscillates as a simple pendulum with a period of 2 seconds. If the planet is taken to the moon on planet X, where free fall acceleration is half as big, that period should be 2.8 seconds, because period here is going to be proportional to 1 over the square root of gravity. Just some tactics in order to find identifying and analyzing your simple harmonic motion. So you can look through those. Those are in your book, on your online book. And then the last thing here that we can look at is the physical pendulum. So if I have any solid object and it's swinging back and forth under its influence of gravity, we call this a physical pendulum. Remember, with physical pendula, we're looking at the center of mass here, and we're not looking typically at the end of the rod. So gravitational torque here is for small angles. We can say is just negative mgl of the angle instead of using the sine of the angle, since we're using small angle approximation. So if we plug this into Newton's second law for rotational motion, torque is equal to I times alpha. We find the equation for simple harmonic motion for a physical pendulum, and that's going to be the square root of mgl all over I, where I is the moment of inertia. So here we go, we've got a swinging leg, and we're going to use this as a pendulum. The student in a biomechanics lab measures the length of his leg from the hip to the heel, which is about 0.9 meters. They want to know what is the frequency of the pendulum of the student's leg and what is the period. We can model this as a rod uniform cross-section pivoted at one end, and so the center of mass of this uniform leg should be just the length divided by 2. So the moment of inertia of a rod pivot at one end is 1/3 ml squared, so the pendulum frequency here is going to be mgl, that's the length, over I. That's 1 over 2 pi times mg. Now remember, we said the length here, center of mass, is L over 2, and then we have 1/3 ml squared for our I value. We can go through, cross off our m's. You'll notice that one of the L's goes away on the bottom, which completely gets rid of the L on the top. The 2 now goes to the bottom, and the 3 comes to the top, and the G stays where it is. So here we've got 0.64 hertz, and so the period is 1.6 seconds. Okay. Notice we didn't need to know the mass, so this is one that we don't have to worry about the mass. I've got a solid disc and a circular hoop. They have the same radius and the same mass. Each can swing back and forth as a pendulum from a pivot on one edge. They want to know which one has the larger period of oscillation, and it's actually the circular hoop. Even though we don't worry about the mass, because they have the same mass, we do worry about their moment of inertia, and because this one has a larger moment of inertia, then it will also have a larger period of oscillation. The last section here is called damped oscillations. Any oscillation that runs down and stops is called a damped oscillation. So that's a good thing if you think about the shock absorbers on your car. They are damped. If they weren't, your car, when it hit a little bump, would just continue to pop up and down all the time. One possible reason for the dissipation of energy is the drag force due to air resistance. So if you think about a pendulum, as it swings back and forth, there's several things that give it friction. One of them is just the friction here at the pivot point, but the other one would be the force due to drag. So the drag force. So the forces involved in dissipation are very complex, but we can use the linear drag model, and we've talked about this before, where we have drag as just negative BV, where B is a constant and V is that velocity. So that's the model for the drag force. Um, if I have a mass on a spring and it experiences the force of the spring given by Hooke's law as well as the linear drag force, so here we have absolute value of the drag is equal to BV, so we got rid of our negative. Our solution is this equation. So this is the equation for a damped harmonic oscillator. The angular frequency is given by this equation. So we can say the angular frequency is equal to the square root of k over m of that undamped oscillator. So that's where you wouldn't have any dampening at all. This is a good picture of kind of what it looks like. So here we have our initial amplitude, and notice that we will never get back to that initial amplitude as long as there's some dampening going on, and that kind of continues all the way through. Damped oscillator has a position. X is equal to x max times the cosine of omega t plus that phase constant or that phase shift. Then we have to make sure that our x max for that position for that period time t is amplitude times the value e negative bt all over 2m. So this is a very slowly changing function. X max provides a broader range of oscillations, and we call that the envelope. So when energy is conserved, there's no dampening. A smaller b causes less dampening. If we get a bigger b, we get more dampening as it goes through. And these are different envelopes is what we call these for dampening. Exponential decay is kind of the same type of thing that you would see there, so I'll let you kind of go through it. Because of the drag force, mechanical energy of damped system is no longer conserved. So we can no longer say that your energy is going to be conserved. Obviously, it's dissipated into friction and some other things. And there's a time constant that you can use for this, but we will not talk about that time constant. Driven oscillations and resonance. If I have an oscillating system that when I leave it to itself, it oscillates at its natural frequency. If I have this system subjected to periodic external force, we call that a driving frequency. So a singer or a musical instrument can actually shatter a goblet or any other glass instrument here by finding its natural oscillation frequency and using that driving frequency to make it vibrate until it is done. So here is the response to a curve. The response curve shows an amplitude of a driven oscillator. So I'm driving this frequency closer and closer to its natural frequency of 2 Hertz. Once I do that, I can shatter that glass is essentially what's going on. The B values here are very different. So a lightly damped system has a very tall and very narrow response curve. A heavily damped system, so one that has a bigger B value here, has very little response. So you can make those damps. You can actually dampen this down to where you're almost going to get that straight line if you want to do that. So here it says the graph shows 3 oscillators and how they respond to the frequency of a driving force. If each oscillator is started and then left alone, which one will oscillate for the longest time? And this one, you would have the red oscillator will oscillate for that longest time because you have more driven oscillation there. And that is the end of chapter 14.